In this video, lesson 1A.7, we're going to be talking about an introduction to proofs. So we're going to explain what a proof is first. In geometry, we often work on problems where we have to not only solve a problem, but we have to kind of give a description of why we get to the answer that we get, or why something is the way it is. And that's a proof. We are proving that a given statement leads us to another conclusion. And you have to think of these as a logical chain of statements. One statement gets you to another statement, gets you to another statement, gets you to another statement, and we can chain these together so someone could follow our logic. And there's a lot of different kind of proofs that we're going to write, but we are solving problems here. In this case today, solving equations using certain rules, and we're listing out the reason for each of the statements that we make. And so we are constructing today something called two-column proofs. And so here's what a two-column proof is. A two-column proof is where the steps of the proof, or whatever problem you're working through, are listed out on the left, where each step is a logical statement we get from the previous statements. The reason for each step is given to the right of each step. And so there are certain things we can use as reasons. And most of the time, there are certain kinds of mathematical statements that have special names, and you cannot just use anything as a reason. We have certain reasons we get to use. Even if you don't remember the exact wording, there are certain ways you can say the reasoning that works. Okay? The very first type of thing, or the very first word we get to use as a reason is the word given. It's just the word given. And what that means is this is the given starting point of my proof. This is the given statement that I'm starting from. It's accepted as true just because it is what is given to you in the problem. But other reasons might include certain properties that we're going to look at today, or certain definitions of terms. You know, that's what the word means. And then there are two other new words here we're going to throw at you. And that is the first word being postulate. Postulate. P-O-S-T-U-L-A-T-E. The word postulate, another word for that is axiom, which we're not really going to use. Axiom with an M. But the word postulate is a kind of like a mathematical definition of a different term, but it does not have to be proven true to be used. But then the other word we have is the word theorem. Kind of like, you've used that before, the Pythagorean theorem. But there are a lot of theorems we can use. And theorems are a lot like postulates. They're these mathematical statements. But in order to use a theorem, it must be proven true to be able to use it in another proof later on. So those are the things we can use for reasons in a proof. So let's first look at some properties. And so in order to save some time on this video, I'm going to write these out with the recording paused. So you're going to see them all appear at once. And then I'm going to explain what each one means. And as I explain it, you might need to pause the video to copy them down. Okay? But here are some of our properties we're going to look at. Okay, there's a lot here. We're actually going to come up to these two in a minute. We're not quite there yet. Let's talk about these. And these first four are just what we use when we solve equations. We've done this before, but now we're going to give a reason. We're going to write out a reason for every step of a proof, kind of like we're giving a detailed description of what we're doing to solve the equation. And so as we look here, we have these first four, which are considered properties of equality. Okay, property of equality. Property of equality, property of equality, property of equality. Okay, those are all properties of equality. And so we're actually going to abbreviate that notation when we talk about these. So we'll write that, and then I will read through these examples, because if you're looking at all of this at once, it's really confusing. So the addition property of equality we can abbreviate as add P-O-E, property of equality. That abbreviation we're going to use a lot today. So all that means is the addition property of equality basically says both sides of an equation are still equal if you add the same thing to both sides. So when we solve an equation by adding something to both sides, kind of like this example here, when I have x minus 2 equals 7, and I add 2 to both sides to get x equals 9, I've used the addition property of equality. So my statement in my proof might be this, And then the reason I put out beside it is add POE. Okay, and so we'll go through how to do that when we do an example of a proof. Okay? Same thing with addition, we have the subtraction property of equality, and so we have to abbreviate that, SUBTR, not just SUB, and I'll tell you why as we get down the list, but subtraction, POE, property of equality. That's when you subtract the same thing from both sides of an equation. Again, pause the video at any time to copy this down. All right, I'll let you see the full page, and then keep playing through. When you multiply both sides of an equation by the same thing, like in our example here, where I multiply by 3 on the left and by 3 on the right, I'm using the multiplication property of equality, or mult, period, POE. Same thing for dividing something on both sides to solve, like the example, dividing by 3 on both sides to get x equals 4. The reason is division, POE. Okay, and so those are our properties of equality for solving equations. We're going to use those. We have another couple properties we have used before that I want to illustrate. The distributive property, which all you have to do is abbreviate DIST for distributive, and then technically this isn't a property of equality. We don't need to say of equality, we can just write prop. It's the distributive property. It's the only one like that, so we can just simplify that down. And when we distribute into a set of parentheses to get something like this, turning 3 parentheses x minus 4 on the left to 3x minus 12, that is using our distributive property. We would give that as a reason. We also have the idea of something called the substitution property. Now, in your own terms, the substitution property refers to the phrase plug in. We've been doing that quite a bit. So if two values are equal, if we say a equals b, then a can be replaced by b in any expression or equation. And we've done that a lot with some of these problems. In the problems where you had to solve x and then find the length of segments, like AB, if AB is x plus 3 and we found x equals 2, we would substitute the 2 in for x to solve and get 5. That's using substitution. Okay? And so those are some of the properties we're going to use. There is one more property we want to use here. Sorry, 2 more at the top. We haven't talked about those yet. We'll come back. Okay, 2 more at the top here. One of them is called the reflexive property, and it again is, in this case, a property of equality. So we want to say the REFL, reflexive, POE, simply states that something equals itself. It doesn't appear that this would be very useful to say that A equals A. It will be useful later on in other lessons. Then we also have something called the symmetric property. And so we can abbreviate SYM, POE. And that says that if A equals B, then B equals A. And we use that anytime we turn an equation around. So if we're ever solving an equation, but when we solve it, for some reason we get 3 equals x, well, you guys get used to just turning that around to x equals 3. You're using the symmetric property. When you flip an equation around, left to right, it is using the symmetric property. Now, like I said a moment ago, there is one other property we want to talk about. So make sure you have this all copied down. There's the full page if you need to see anything. Pause the video, copy it down. Otherwise, go to the next page, and we have something called the transitive property. The transitive property states if one equation is like A equals B, and another equation about B is that B also equals C, well, we know A equals C, and we can actually chain that together with a bunch of them. A equals B, B equals C, C equals D, D equals F, all the way on out. We could eventually say A equals F to shorten that up. And that is called the transitive, or trans, POE. Transitive property of equality. So now we're going to actually practice writing some proofs. All of these are considered algebraic proofs. Algebraic, meaning pertaining to algebra, just solving equations. So we're going to start off with a given equation, and we are going to prove the answer. Now, this seems strange, I know, to you, because I'm giving you an equation and I'm giving you the answer. Getting the answer is not the point. The point is explaining how you get to the answer. So we're going to write a proof. And so the first thing we want to always do in a two-column proof is we always start with the given statement. And these statements is where we do our work. It's where we show that work. The reasons explain why. So the first statement is always whatever is given to you. So I copy it down. 5 parentheses, x minus 12 parentheses equals 2 parentheses, 2x plus 30. Close your parentheses. And the reason I can write that is that it is given to me. That's the only reason I can write that equation on paper, is because that's my starting problem, the given. That is always your first reason. Then we start to do the work. Now here's where this is a little bit different. I'm actually not going to show separate steps. I'm going to show the result of the next step. The result of the next step, if I wanted to show it, I could do my distributing lines like that, but I'm actually not going to include those in on that line. I'm just going to show what I would get. When you do 5 into the first parentheses, you get 5x minus 5 times 12 is 60. Bring your equal sign down, distribute the 2 on the next side. 2 times 2x is 4x. Distributing 2 times 30 is plus 60. Okay? And the reason I can do that is because I use the distributive property. So I write distributive property. Now, you need to remember, the reason tells you how you got this statement, not what you're going to do next. The reason always goes back and tells you what the line before it is about, not what you're going to do next. What I am going to do next is get the x's on one side. So what I would do is subtract the 4x from both sides, but I'm not going to show that. Okay? I'm even going to show you that I'm erasing that. I'm not going to show that. There, get my eraser to work right. What I'm going to do is show what would happen if I did subtract 4x from both sides. On the right side, it cancels, so the only thing on the right side is equals 60. On the left side, 5x minus 4x is just x, and I still have my minus 60. Please be careful as you look at this. A lot of you are going to look at this and think, oh, the 60s cancel. They do not, because they're not the same number. Let me go back and finish this step. In order to get x minus 60 equals 60 from the previous statement, I subtracted 4x from both sides. When you subtract from both sides, that is the subtraction, P-O-E, property of equality. Then, to move forward, to get x completely by itself, we would add this 60 on the left to both sides. Again, I don't need to show that. I'm just going to show what I get in that process. When you add 60 to both sides, it turns this into 120 on the right, x on the left, which is what I was trying to prove, and that's why it's the last line. But the reason I ended up with x equals 120 from the last step is that I added 60 to both sides, so it's the addition, property of equality. Okay? And you have just written your first proof in geometry. And so let's go ahead and take a look at another example. We're going to do another proof. It's a little bit longer because we have a little bit longer equation to work with. But we want to prove that x does in fact equal negative 1.5. And so again, the first thing you do is write this statement after the word given. That equation goes in the first blank, 5 parentheses x minus 2 plus 2 minus x equals 2 parentheses x minus 4 minus 3. And that is the given statement, or the given equation. And so the first thing you want to do is try and figure out how to solve the equation. Well, you should recognize the first thing to do is distribute. So we can do that on both sides. Excuse me. When we distribute on both sides, it turns the equation into 5x minus 10 plus 2 minus x equals 2x minus 8 minus 3. And the only reason I can get that is because I distributed. So my reason is the distributive property. Again, your reason has to tell you how you got that line. The reason goes with getting this line, not what you're going to do next. Now, to simplify this further, there are like terms on both sides we can combine. We can do 5x minus x is 4x. Negative 10 plus 2 is minus 8. And on the right side, we have like terms negative 8 and negative 3. So that becomes 2x minus 11. Okay. And then we are going to write a reason that we were able to get that. When you combine like terms, all you really did is simplify. We did not add something to both sides of the equation. We didn't add the same thing to both sides of an equation. We didn't subtract the same thing from both sides. So we can either write simplify, or you can even write the phrase combine like terms. So C-O-M-B for combine, like terms. You can use that as a reason also. And let's keep going. Now we want to get the variable alone on one side, and to finish our proof, we do want the variable on the left, so we try and keep it there. So we're going to subtract 2x from both sides. When you subtract 2x from both sides, that leaves you with 2x minus 8 on the left equals negative 11. And since you did subtract the same thing from both sides of an equation, that is the subtraction POE, property of equality. Now we need to get rid of the minus 8, so we would add that to both sides. It cancels it on the left, which leaves 2x. And on the right, negative 11 plus 8 is negative 3. Since we added to both sides, it's the addition property of equality for our reason. And in the final step, to undo 2x, to get rid of the 2, you would have to divide by 2. 2x divided by 2 is just x. Negative 3 divided by 2 is negative 1.5, or negative 1.5. And that is what we were trying to prove. The reason I was able to get that is through the division property of equality. And that completes that proof. And so as we go on to one more example, this is going to work out a little bit differently. We're still thinking of this as an algebraic proof, but it's going to be a little bit more complex. Okay? And so I want you to follow along with this one. We are only given sets of coordinates. We're given A has the coordinates 3, 6, B has the coordinates 0, 10, and C has the coordinates negative 4, 13. And they ask you to prove that that segment AB is congruent to segment BC. Now, in order for segments to be congruent, they must have equal measures, which means before I can say AB is congruent to BC, I need to say that length AB equals length BC. And so what I want to do, I'm actually going to show you how we can fill in a proof from the back towards the beginning. We can start at the end and work our way back up. So we can go ahead and write all the given information as step 1. A is at 3, 6. B is at 0, 10. And C is at negative 4, 13. And that is still my given information. Okay? Now, the very end of the proof is going to be this statement. Segment AB is congruent to segment BC. I don't know this reason yet, and so I'm going to leave that blank. But I do know I have to finish with that. Right before AB congruent to BC like that, I need to say that length AB equals length BC. And again, I don't know the reasons yet. We'll fill that in. But I know I have to say this one before I can say this one. And I'll explain how we work this out as we go. So if I'm talking about the lengths of AB and BC, that means I need to use the distance formula. All right, the distance formula is the square root of x1 minus x2, or I think I gave it to you the other way around. It really doesn't matter. But let's keep it the same. x2 minus x1 squared plus y2 minus y1 squared. Okay? And so we're going to do that for both of these. So in one of these steps, we're going to say AB equals, and we're going to plug in for our distance formula and simplify all in the same line. We can kind of take some shortcuts here. So if I start filling in coordinates for A, B, x2 would be 0 minus 3 for x1 squared, plus, for the y's, I would have to do 10 minus 6 and square that. And I'm going to kind of continue my work here. I have to write kind of small, but I'm going to simplify this. Excuse me. Negative 3, or 0 minus 3 is negative 3. Negative 3 squared is 9, positive 9. Plus, 10 minus 6 is 4, and 4 squared is 16. And if I add 9 to 16, that's the square root of 25, which is a nice, easy whole number, 5. The square root of 25 is 5, since 5 is what we consider a perfect square. Now, that entire line is simply the distance formula. All right, I don't actually have to put that in. It does come from the Pythagorean theorem, so technically I could use that as a theorem. I could say Pythagorean theorem, even though it's kind of tricky to do that. But now I'm going to do the same thing for BC. I'm going to use my distance formula to calculate from B to C. So this time I'm going to do negative 4 minus 0 squared for the x's, and 13 minus 10 squared for the y's. Well, negative 4 minus 0 is negative 4. Negative 4 squared is 16. And 13 minus 10 is 3, and 3 squared is 9. And again, if I add in a different order, 16 plus 9 is 25, which also equals 5. Again, the same reason. Distance formula. Now, I want you to notice that in these two lines, I've said AB equals 5, and BC equals 5. Since AB and BC both equal 5, AB has to equal BC. This is kind of what we've said. AB equals 5, and 5 equals BC if I flip that around. So, AB has to equal BC. What we've just used is the transitive property of equality. Or you could also call this substitution. We're substituting AB in for 5, since 5 equals BC. Okay? The proof itself is just what's in these boxes. All this extra stuff outside of the boxes is just my instruction, my helpful hints. Now, since these are congruent or equal values, equal lengths, they must be congruent segments because that's what the word congruent means. Anytime you can say that's what that word means, you're using a definition of that word. So this is the definition of congruence. Anytime we use statements like this, in any order, either in this order or this order, sometimes we flip that around. Anytime we group those two together, the reason you can say the last one is the definition of congruent. So that concludes how to start doing some proofs. Most of them are going to be like these proofs, just solving equations and giving a reason for each one. We will eventually get to more complicated proofs, though.